This is 2.7 and 2.8 notes. Starting with 2.7, combining functions. Number 1 says let f of x equal 1 over x minus 2 and g of x equal the square root of x. So we have a rational function and we have the square root of x, and we are going to combine these to find the domain. And some of these might be an intersection. All right, so let's look at this. This means exactly what you think it is. We're going to add the two functions together. And if we add the two functions, we've got 1 over x minus 2. And if we add the square root of x, there's nothing that we can do with these. This is actually the answer. And if we want to find the domain, on this first one, if you want to find the domain, then basically x cannot equal 2. And on this one, x has to be greater than or equal to 0. Whoops, 2. Sorry about that. And x has to be greater than or equal to 0. So we write the domain for this. Then I would say that that 0 is included, and we're going to go to 2. Then we would union 2, and we would go to infinity. Okay, for this one, when we want to subtract the 2, then I would say that 1 over x minus 2, and we're going to subtract the square root of x. And again, I cannot combine these, so this would be my answer. So again, x cannot equal 2, and x has to be greater than or equal to 0. So it looks like my domain is going to be the same. Right here, this means I'm going to multiply the 2. So if I multiply the 2, then get the square root of x over x minus 2. Okay, because this is on the bottom, x still cannot equal 2. I still need to worry about this function right here because I've got a square root, so x still cannot equal 0. It looks like my domain is still staying the same. All right, when I divide f by g, so my function f by g, it looks like I need to leave, change flip, so I can just multiply by the reciprocal, and I'm going to have 1 over root x times x minus 2. Now because this is on the bottom, I no longer can be equal to 0, so x has to be greater than 0, and x still cannot be 2. So the only thing that's going to change with my domain now is that I can't have a bracket, so it's going to be all parentheses, and that's the only thing that changes with my domain. But the most common mistake here is that everybody distributes a 4. When you have a 4 outside, this means that you're going to substitute the 4 in for x. So take your f function. Your f function is x minus 2. Replace the 4 in for that. I'm going to add my g function, which is the square root of x, and I'm going to replace the 4 in for my x. So I'm going to simplify this. That gives me 1 over 2, and I'm going to add the square root of 4, which is 2. I'm going to add that together and get 2.5, or that is 5/2. And that's your final answer. This next section, it says if your function f of x is x squared and g of x is x minus 2, find each. Well, first of all, these are composition functions. And another way that you might read this or see this is f of g of x. And another way that you might see this is read like this or seen like this with a little bitty o and a g. So you might see this as fog, and this is g of f of x. And you might see this as goth, okay, with a little bitty o in the middle. Okay, if I see this as f of g of x, the first thing you need to do is replace this g of x. So I'm going to start with f and replace the g of x in the middle. So I'm going to replace that with x minus 3. So if I take my f function and replace that, so now take your f function, which is x squared, and replace that. So now I'm going to have x minus 3, and I'm going to square that. So you're going to double distribute, and that should be x squared minus 6x, and that would be plus 9. That's all you need to do. Okay, on this one, I'm going to go from the inside, my g of f of x, replace my f of x inside. So I'm going to have a g, put your f of x inside, so that would be x squared. Now bring my g of x down. So my g of x is x minus 3, and I'm going to replace that. So I have an x squared minus 3, and I can't do anything with that. Now if you notice that these are different, these are not equivalent. If they were, they would be inverse functions, and I will actually get into that. The domain of f of g of x is the intersection of the domains of g of x and f of g of x. It says let f of x be the square root of x and g of x be the square root of 2 minus x. So it says find g of f of x. Now remember, this means g of f of x. So the first thing I would do is take your g and plug in your f of x here. So this is the square root of x. So that means you've got 2 minus x. So when you plug in your square root here, this means you have 2 minus the square root of x. And this doesn't simplify, this is it. So now we need to find the domain. And in order to do that, you need to find each square root. So to find the square root of this one, to find the square root of, or to find the domain of this, you just take x, and that's going to be greater than or equal to 0. And then you need to take this whole thing and do the same thing. So you're going to say 2 minus the square root of x is greater than or equal to 0. So negative x is greater than or equal to negative 2. I would divide by negative. So the square root of x is going to be less than or equal to 2. Let's see, let's square everything. So that gives me x is less than or equal to 4. And if we combine both of these, it looks like your domain for everything is going to be 0 to 4. And that would be everything. See what this says. It says if h of x is this function, find f and g such that h of x is this composition. Okay, now there's a bunch of functions that we could come up with, but I'm going to try to come up with the easiest one possible. So I'm going to come up with a g of x, and I'm going to come up with an f of x. So my g of x is the inside. So what could I have plugged in on the inside to get this composition function? So I'm going to try, maybe if I plugged in an x plus 9 and I made my f of x the fourth root of x. Let's do another one, g of x. And again, I'm doing the most simplified version that I can come up with. If I did g of x, I'm going to say that this is an x squared minus 8, the whole denominator, and then I'm going to say this is a 5 over x. Let's look at inverses, which I've already kind of talked about. If f of x has a domain a and b, then f raised to the negative 1 means the inverse of f. This right here, anytime you see a negative 1 means inverse, okay? Has a domain of b and a range of a. So basically, you're flipping your domain and range. Flip domain and range. The graph of your inverse has a reflection of f of x across y equals x. And hopefully you have remembered that or have heard that before. If f and g are inverses of each other, then f of g of x equals x, and g of f of x also equals x. Okay, so let's look at this down here. It says let f of 1 equal 5. What this means is this is your x value and this is your y value. So this is input, this is output. Again, if x is 3, then y is 7. If x is 8, then y is negative 10. Now let's look at your inverse. If the inverse is 7, that means if your x is 7, what is your y? Remember, you're flipping your x and y's. So if this is your x, what is your y? So I'm going to look up here. If this is your x, then this is your y. So it has to be 3. What is your inverse of 5? So again, I'm looking at my y values to find my x, and it looks like it has to be 1. Okay, those again, if you're flipping your x's and y's, if I want to find my inverse up here, then what I need to do is to take this right here and substitute it in for y. This gives me x to the 5th minus 3 over 2. All you need to do is flip your x's and y's. So this is x equal y to the 5th minus 3 over 2. And you need to solve for y. So that would be 2x equals y to the 5th over 3. Go ahead and add 3. So that's y to the 5th equals 2x plus 3. And then take the 5th root. So y equals 5th root of 2x plus 3. And that would be, well, let's go ahead and write it as a inverse function of x equals y to the 5th root of 2x plus 3. So that I know that it's the inverse function. Okay, one thing that you need to check for is your domain. Like in the last unit, we checked for restrictions or extraneous solutions. We're going to check for domain. And this is what you need to do. Remember, your domain and range are flipped. So if I check for my domain here, this has a 5th root. So any odd integer or odd exponent is going to look like your cube root. It just changes the number of humps in here. So this domain and range, both are all real numbers. Okay? So no matter what, if I flip my domain and my range, it's all real numbers. So when I look down here at my inverse, my domain and range are still all real numbers. So I have to think about any restrictions on this problem. On number 3, I do have some restrictions. So let's solve this. This is y equals x, the square root of x minus 2. Flipping your x and y, this is x equals the square root of y minus 2. I need to square both sides. So this is now x squared equals y minus 2. Add 2 to both sides. So this is x squared plus 2 is equal to y. Making this look like an actual inverse problem, f to the negative 1 of x equals x squared plus 2. And now this is written as an inverse problem. Okay, now I said there was a restriction on this. Looking at this right here, I'm going to sketch a little graph. This is the square root function minus 2. So the square root function looks like this. Minus 2 would be over 2. So this problem looks like basically that. My inverse function was a parabola plus 2. So let's look at parabola plus 2. So basically like this. Okay, these are supposed to be inverse functions. Inverse functions reflect over y equals x. Well, this definitely is not a sideways parabola, so these are not quite inverse functions. But in order to make it an inverse function, this right here could be an inverse function if I only had this part right here. So I need to get rid of this. So in order to make them inverse functions, I could say this is an inverse if x was greater than or equal to 0. So I'm going to add that on to this problem to make them true inverse problems. Okay? A graph is said to be 1 to 1 if there are no repeated x values, passing the vertical line test, and no repeated y values if they pass the horizontal line test. Okay, so let's look down here. Is this function, is this a function first of all? And I would say yes. Is the inverse a function? So if you were to draw a line anywhere on this, could this be a function, the inverse? And I'm thinking this one is not. So going back up here to number 4, is this a 1 to 1? And I'm going to tell you this is not. If either one of these is a no, then it is not 1 to 1. And that's how you can test that out. Okay, so now I'm going to ask you this question. Which parent function has a 1 to 1? And this is one of them. This is y equals x cubed. So that gives you one of them. Which parent function is 1-to-1? All right, so we know x cubed is one of them because we already wrote it out. We've already talked about x squared. We did it in the previous problem, so x squared is not. Y equals x is 1-to-1. So here's x cubed, that is. Y equals x is. How about the square root of x? Here's the square root of x, looks like this. That is 1-to-1. Exponential. Exponential looks like this. And if you don't remember the graph, this would be exponential. Since exponential is, its inverse also is. That would be natural log or log, as some of you remember. And it looks like this. And then there's one more, and it's the funny graph that everybody thinks is strange looking, and it's rational. Rational graphs look like this. They go in the first quadrant, and then they go in the fourth quadrant. And those are 1-to-1 graphs.